Hi there, welcome to my dog classification model for learning data coursework. So, for a bit of an introduction, the research question proposed, due to the light of what's happened recently, is the impact of deep machine learning to effectively differentiate between different dog breeds. Considering the UK government's recent expansion of the UK dogs ban list. So the significance of this research question lies with its ability to assess the influence of advanced machine learning models on diverse facets of human society. A recent update by the UK government expanded the list of banned dogs to include XL bully dogs. So they have made this rule since the 1st of February 2024, where it'll be a criminal offence to own a XL bully dog in England. Given the varying levels of aggressiveness among dog breeds and their differing rates of human attacks, it is crucial to establish legislation and policies governing dog breeding and identification. This becomes even more pressing considering the substantial exponential growth of deep learning and neural networks, particularly in the domain of convolutional neural networks. Just within the past couple decades. So this presents an opportunity to practically explore how deep machine learning models can positively contribute to assisting society. So, the dataset. So before we make a model, it's very important to talk about a dataset because that's based upon everything within machine learning. So current literature consistently recognizes the effectiveness of a machine learning model, fundamentally limited by the quality of the data that it relies on. Many authors in the overview and importance of data quality for machine learning tasks, it's a research paper, provides a clear outline on how to be selective with the dataset. Henceforth, the dataset that will be used to create a CNN model will have to be critically analyzed before the use. So, after research on a large dataset platform, so I went on Kaggle and GitHub, the chosen dataset for investigating the research question, I ended up landing on the Stanford dogs dataset, which stood out to be a more preferable option compared to others such as the Qinghui dog dataset. And the main reason is the attractiveness of the Stanford dog dataset primarily lies in its extensive amount of curated data, boasting 120 categories and a total of 20,580 images. Additionally, this dataset comes equipped with labels and bounding boxes, which is conveniently provided by Kaggle. So upon closer examination of the dataset, it is evident that the images within it are predominantly consist of frontal shots capturing the faces of dogs, which you can see on this slideshow here. And this exhibits a range of angles and lighting conditions, which is phenomenal. So this variable alone significantly influences the accuracy of the model. Considering the division into training and validation sets, it becomes imperative for the convolutional neural network model to grasp diverse features within each classification to prevent excessive overfitting. An additional compelling factor supporting the potential of this dataset to yield conclusive insights for the research question is a piece of literature focused on enhancing image classification titled Stanford Dogs Keras VGG16, authored by Terence Whitehurst. So this was an author that used the Stanford Dogs dataset and produced a model which was very successful. He was able to achieve an average loss of 1.136 and an accuracy of 0.60 on the 11th epoch on his CNN model, meaning he had about 60% accuracy. And the author demonstrated that this dataset is capable of yielding a model performing significantly better than random chance. So this outcome strongly indicates of the dataset's potential to address and resolve the research question at hand. Now talking about CNN models. Lately, there has been a significant urge in the utilization and effectiveness of convolutional neural networks. The paper titled Effective Processing of Convolutional Neural Networks for Computer Vision, a Tutorial and Survey, unmistakably highlights the considerable performance and efficiency of employing CNN tasks for involving image classifications. Therefore, the optimal model to address the research question would be to involve leveraging a conventional convolutional neural network integrated with the most current methodologies available. Now we need to talk about data preprocessing. So, before constructing and testing a model, it is crucial to pre-process and refine the dataset intended for each CNN model. The initial phase involved developing a Python script to traverse each subdirectory of the dog dataset and standardize the images. This process entailed resizing the images to 150 by 150 pixels, which normalized each pixel between the value of 0 and 1, and also assigned these values as float 32. This step was necessary to ensure the consistent data interpretation within the model, facilitating ease of access and uniformity in processing using the model. The subsequent stage comprised dividing the complete dataset into two segments, training data and validation data. An additional Python codebase was developed for this purpose, splitting the overall dataset into 70% of training data and 30% for validation. The random allocation of data ensured that an unbiased distribution between these two segments. So this was done randomly. And you can see the code bases here. So this is for moving the images into one directory, for normalizing, and for splitting up the dataset. So once we have cleaned and pre-processed our data, we need to talk about the model. So you can see down here, this is the model that we have created with all the layers. So after conducting 8 epochs constrained by the computational limitations on my local machine, 2 graphs were generated, one A and one B. The graph depicting pure loss and accuracy reveals a rapid decline in loss after the third epoch, accompanied by a steady increase in accuracy nearing 99%. However, to validate the model's performance, attention was shifted to the validation dataset. In the validation performance model, the validation loss spiked sharply after the initial epoch, while the validation accuracy remained extremely low. This discrepancy indicates severe overfitting, where the model excelled in predicting the training data but struggled to generalize to the validation dataset due to excessive fitting to specific features. This overfitting might be attributed to the choice of batch size of 64 as a hyperparameter, influenced by the computational resources. Influenced by the limited amount of computational resources. Nevertheless, it's noteworthy that our model demonstrated high accuracy on the training dataset, signifying its swift ability to identify distinct dog breeds using provided training data. Looking ahead, with increased computational power as detailed in the slide after this, adjustments to hyperparameters would be pursued. This would involve significantly augmenting the total epochs while reducing the hyperparameters to mitigate overfitting, thereby enabling the model to generalize better to new data. So comparing the models generated to another scholar's model based upon the same dataset, we can see that the graph they had generated was also able to predict it the model that they generated was able to predict it with more legitimized output data. There was a relatively high accuracy with a low loss, which is ideal in this situation, which you can see from Terence Whitehurst over here. So what's the problem with our model? Well, let's talk about some limitations. So my model's limitations, the primary constraint when utilizing and evaluating a CNN model lies in considerable computational resources it demands for computation. The CNN model developed early was executed on my local machine equipped with a multi-core contemporary CPU. Despite the setup, each epoch took exceptionally long, exceeding 7 minutes per epoch. Typically, modern models require training across a minimum of 10 epochs, resulting in over 70 minutes of training time for each adjustment made to hyperparameter. Alongside this, the batch size would be decreased if it had better computational ability, which would hope to dramatically decrease the overfitting on the model that we see. The extensive time required and limited number of changes feasible within the CNN model due to computational constraints emerge as the most significant limitation to its creation and application. Obviously, having a GPU training CNN models would be a lot better. So, moving on to the conclusion. In summary, the utilization of CNN models for dog classification and identification within datasets holds great promise. However, to effectively validate this theory, increased access to computational resources is essential. Ideally, employing a rapid state-of-the-art GPU or TPU for training and testing CNN models would be optimal. If these advancements are pursued and thoroughly tested, significant implications can arise in public surveillance for identifying potentially dangerous dog breeds. Moreover, this technology could potentially extend to assessing human-populated areas, identifying high-risk zones, or predicting crime rates, contingent upon the complexity and computational capabilities harnessed by the CNN. And here are some of my references. Thank you so much.